In the last video, we started taking a look at fluids in motion and explored the consequences of the assumption of incompressibility to obtain the equation of continuity. So here we're going to take a look at how the motion of fluid affects pressure, and this is given by Bernoulli's equation. So I'm going to imagine a rather bizarrely shaped pipe, maybe say something like that. So let's say the speed of the fluid here is V1, and the speed of the fluid here is something lower, V2. So this will be my depth number 1. That will be my depth number 2. So the pressure here will be P1. The pressure here will be P2. All right, and similarly, we can have some reference line, say here, and we can go ahead and say that our, our height here is Y1, and our height here is Y2. Now, in an earlier video, when we were looking at fluid statics, we'd realized that Pascal's principle can be written not just as a statement about forces, but also a statement about energy density. So remember, the guiding principle here is that the energy density of a fluid has to be the same anywhere. So we had already seen that the pressure was related to the thermal energy density, and we had a term rho g y1 effectively in Pascal's equation, and we interpreted this as that since this is a mass over volume, if this were mass, this would be mgy, that'd be a potential energy. So this corresponded to a potential energy per unit volume. So if we could stick in something that looks like a kinetic energy per unit volume here, that would express the energy density at this point right here. Well, we can. The kinetic energy of a mass of fluid going through here would be 1/2 mv squared. And if I divide the mass by the volume, I would again get the density. So be very careful. This is a P, these are rhos. But this is saying that the total energy density at one location would be the total energy density at another location. And so that's Bernoulli's equation. So it just says that the energy density is the same everywhere, but now we've taken into account the motion. So let's go ahead and look at, say, an example here where I've got a pipe coming in, will flow out a constriction like that, pipe flowing out. We'll say that the change in elevation on the pipe is 10 meters. That should be to the center of the pipe. Let's do a better job drawing that. All right. So let's say the fluid here is moving at 3 meters per second. So that'd be my V2. And the fluid here is moving at 2 meters per second. So that's my V1. Let's say the pressure here, P1, is 200 kPa. What I want to know is what's the pressure over here. Well, just like with all things potential energy, we're free to choose where y equals 0 is. So let's choose it there. So y1 equals 0 there. We'll make y2 equal to 10 meters there. And that will simplify my Bernoulli's equation expression at least a tiny little bit. And this is the name of the game with Bernoulli. This is probably about the most complicated example you'll ever see Usually the name of the game is to make as many things cancel as you possibly can and look at what's left. So for instance here, we can then go ahead and say, all right, whoops, P2 plus 1/2 rho V2 squared plus rho G Y2 equals P1 plus 1/2 rho V1 squared plus rho G Y1. And since we set Y1 equal to 0, at least that term drops. Solving for P2 then, we'll have that's P1 plus 1/2 rho V1 squared plus minus 1/2 rho V2 squared minus rho G Y2. So we can pull out a row from everything just to clean up a little bit. So rho V1 squared minus V2 squared over 2. Sorry, I forgot to mention this is water. Or maybe I did. Minus G Y2. All right, so we can put that all in. We said it's 200 kilopascals, so they'll have to be turned into pascals. Plus 1,000 kilograms per cubic meter times 2 meters per second squared minus 3 meters per second squared over 2 minus 9.8 newtons per kilogram times 10 meters. Grind that all through, you get 99,500 pascals, or 99.5 kilopascals. So you can see that, probably unsurprisingly, if you make a fluid go uphill, it tends to drop pressure quite a bit. And this is a real concern for designing city water distribution systems. This is why you have water towers. The point is you pump the water way up to some big height that increases the gravitational potential energy density there, right? And that increases the energy density of the fluid everywhere. And that allows you to still have decent water pressure even if a fluid has to go up a hill or up several stories in a building, or up a hill and several stories in a building. You get the idea. So another example of where an increase in speed will give you a decrease in pressure is a fun demonstration that you can try yourself at home. Just find any old 2 little slips of paper, leftover receipts or something like that. Hold one in each hand. Bring them about a couple centimeters away from each other in front of your mouth, and then blow between them. What happened to the receipts? Seriously, go ahead, try this, get back with me. You probably saw that the receipts actually blew together. So what happened with that? Now let's look at one slip of paper here, and then we'll have another slip of paper, say, over here. We'll call this region 1 right here, and in region 1 we have air blowing through it at a speed that is definitely not 0. In region 2 on the outside, the speed of the air there definitely is 0. Here, because we're talking just inside or outside the receipts, we can make y1 equal to y2, whatever they are. So we can go ahead and do a little Bernoulli action on this. So P1 plus 1/2 rho V1 squared plus rho G y1 equals P2 plus 1/2 rho V2 squared plus rho G y2. So the air on the outside was still, so that gives us 0. And whatever my y coordinates were, they were the same, so both of those terms cancel. So if I subtract the 1/2 rho v1 squared from both sides, I get that p1 is equal to p2 minus 1/2 rho v1 squared. So the air between the receipts has lower pressure than the air outside the receipts. So on net, there will be a force due to pressure on the receipts, pushing them inward. Cool, huh? And we'll finish this last one out with a classic problem that's usually called Torricelli's result. So Torricelli was the person who invented the barometer, and he worked out that for all practical purposes, the Earth has functionally next to no atmosphere on the scale of the size of the Earth. If you shrink the Earth down to the size of an orange, the Earth's atmosphere's thickness would in proportion be the orange part of the orange, and I'm not including the nasty white bit underneath it. This actually solved an age-old puzzle. Heliocentrism was an idea that had been tossed around for a long time before Copernicus revived it. The idea that planets go around the sun. The ancient Greeks were aware that that would have made more sense, but they rejected it because they worked out the rate. They knew roughly how big the Earth was. They knew it to within about 3 or 4%. You can figure that out by looking at angles of shadows cast by sticks at different latitudes. So they worked that out. And so they knew to within a few percent what the size of the Earth was. And they realized that in order for the sun to rise and set, the Earth would have to turn on its axis once every 24 hours. And then they were coming to the conclusion that that meant that moving on the surface of the Earth, about the latitude of Greece or Turkey, you would be facing apparent headwinds that were so severe that would make a Category 5 hurricane look like a gentle breeze. And so they said, well, our buildings are standing, we're not leveled down, so it's a good idea, but it must not have worked. And so they adopted, reluctantly, geocentrism instead, where they imagined the Earth going around the sun. Now, the danger here is when you make an assumption is the assumption you don't even realize you're making. In the case of these ancient Greeks, they tacitly assumed that the universe was full of air. And if it was, their analysis would have been correct. Torricelli, though, by taking his barometer and running up and down mountains and noticing a noticeable change in atmospheric pressure as he went up and down mountains, worked out that the Earth's atmosphere was actually a very, very thin thing indeed. And so as the Earth rotated, it wasn't a big deal for the air to more or less rotate get drug along by the Earth and rotate with the Earth, thus taking care of that headwind problem and post hoc helping to provide support for Copernicus's idea, since Copernicus mostly went with it for computational convenience. Anyway, all that being said, Torricelli, before the ideas of energy density were completely worked out, reasoned in a way that was almost but not quite an energy density argument. He got to think about, what if you have, say, a large cask full of your favorite beverage. And let's just say it's open to air on the top. And let's say it's a very large cask. So we'll say that this height here, we'll say this is height 1, this is height 2, this is 10 meters. So we'll make y1 equal to 10 meters here, and y2 equal to 0 meters here. Again, just choosing 0 at the bottom of the problem to make some of the Bernoulli stuff cancel out. He was then interested in how fast is the fluid exiting this small constriction right here. And at first blush, it seems like you don't have enough information to answer the question, and that is correct. However, you can approximate it pretty well. If we appeal to continuity, continuity says that the volumetric flow rate at depth 1 would have to equal the volumetric flow rate at depth 2, or A1 V1 equals A2 V2. So V1 would be equal to A2 over A1 times V2. Well, if this is a small constriction and this is a big cask, A2 would be equal to darn small, and we would be dividing that by darn big times V1. And darn small over darn big is approximately 0, so we'll just say that, if we're just trying to get to the first decimal place or two, we can get away with saying that we know the fluid is moving, but we can approximate it in this particular case as being very slow compared to how it's exiting, and so we'll just make it 0 to make the problem easier to do. Torricelli reasoned in a situation like this that you could think about it as if the fluid were just falling down like you were dropping a rock. And so he came to the conclusion that it would be root 2gy, which is correct. And he argued it more from a kinematics perspective than anything. But let's go ahead and do it right with Bernoulli. So Bernoulli is going to say P2 plus 1/2 rho V2 squared plus rho GY2 equals the same thing with ones. Well, here, the other question is, what's P2? Well, P2 turns out to also be 1 ATM. Isn't that convenient? It's open to air here. It's open to air here. It's open to air there. P1 and P2 cancel. We've approximated V1 as being nearly 0, so that term goes out. And we've set Y2 to be equal to 0, because we're allowed to do that. So we are left with 1/2 rho V2 squared equals rho GY1. So hey, it doesn't matter what your favorite beverage is, the densities cancel. Sorry, you still can't do a Wendy's Frosty because we're neglecting viscosity here. But otherwise, we're going to get that V2 squared is 2GY1, and V2 is equal to root 2GY1, which is exactly what Torricelli reasoned from his pseudo-kinematics idea. All right, well, let's just go ahead and put in the numbers here. So this will be the square root of 2 times 9.8 newtons per kilogram times 10 meters. And here it'll be more useful to express a newton per kilogram as meter per second squared. So you have meters squared upstairs, you have seconds squared downstairs. Take the square root of that, and you will get meters per second, so that's all good. And you will get about 14 meters per second. Again, as long as it's not a Wendy's Frosty or something crazy like that, something with low viscosity, it doesn't matter what the fluid is, that's the rate at which it should be leaking out the hole at the bottom.